All right, so today we'll start the subject of electricity. Okay, we'll study electricity and magnetism. Maybe you can unlock it. Okay, so we'll study electricity and magnetism. Okay, so here's the deal. So in the next 7 or 8 chapters, we'll study electricity and magnetism. Okay, what you'll learn is if you have a stationary charge, it produces an electric field around it. Okay, and electric fields are denoted by E. Okay, now if you have a moving charge that is moving, now this charge produces electric field as well. And in addition, you will learn, if it's moving like that, now you'll learn this a few chapters from now, it will produce magnetic fields as well. Okay, so moving charges produces both electric and magnetic fields. And I'll tell you the configuration of this magnetic field. Well, so the configuration of this magnetic field is as follows. If you have a, okay, so let me draw that. So if this is the charge traveling in this direction, there's the velocity. Imagine a cylinder around it, centered around this axis, and the magnetic field is tangent to this cylinder. Okay, and this, if you point your thumb in this direction with your right hand, your fingers will point in the direction of the magnetic field. Okay, so if you point your thumb like that, the magnetic field will be like this. Okay, so here's a very interesting point. Now think about this before you answer the question. So we said a stationary charge produces only an electric field. A moving charge produces an electric and magnetic field. All right, so now let me draw another situation. Okay, so this is you standing. What do you see this thing is producing?
Electric field.
An electric field. And this is your buddy driving in a car. What does he see?
An electric and a magnetic field.
Exactly. So this guy sees this charge as moving in this direction, okay? And so he sees an electric field, he'll see a different electric field like that, and a magnetic field that's pointed in that direction, okay? So the electric and magnetic fields are sort of the same field. It depends what you see depending on your relative motion, okay? So what this guy sees as purely electric field, this guy sees it as a combination of an electric and magnetic field, okay? All right, just keep that in mind. All right, so anyway, that's a higher level concept, but I just wanted to mention it, okay? So even though they're unrelated, they are really cousins, okay? So what we'll do is, so we saw that a stationary charge produces electric fields, okay? And a moving charge produces both electric and magnetic fields, okay? So the way we'll start off this stuff is we'll consider stationary charges. We'll study electric fields. For the first 4 chapters, we'll study stationary charges in various configurations. Then we'll look at moving charges, and then we'll study just the magnetic field part of it. Okay, and we won't bother about the electric fields. Okay, all right. So that's the program. All right, so these 4 chapters, in these 4 chapters, we'll consider charges that are stationary. And then we'll get the charges to move. Okay? And then we'll study circuits and stuff like that, and we'll study the magnetic field effects of that. Okay? So that's what's coming up the next 7, 8 chapters. All right. All right, so here's how you can charge particles in practice. Okay, so what I'll do is I'll draw you a model of an atom. Okay. So I'll draw a simple atom. I'll draw the lithium atom. Lithium atom has 3 electrons to it. Okay. So here's the nucleus of the lithium atom. Okay. All right, so there are 3 protons, 3 neutrons, and 3 electrons. Okay, the outermost electrons are called the valence electrons. Okay, and generally those are loosely held, and those are the ones that get involved in chemical reactions. So all of chemistry is about messing with those electrons. You're never touching the inner electrons. Okay. Now here's the deal. Some atoms are hanging on to them strongly, and then some atoms don't hang on to them as strongly. Okay. So if they're hanging on to them strongly, what does that mean? They don't interact chemically as easily. If you're hanging on to them only lightly, then you react with everything. Okay. So for instance, the first column elements, they have only 1 electron, and they don't hang on to them very tightly. They're willing to give it up very easily. Yeah. The last column, the noble gases, they have a full valence electrons shell. Okay. So they don't want extra electrons, or they don't want to give up any extra electrons, so they never react. Okay. The one before that, the last but 1 column. Okay, so I'll draw one of those guys. And I'll draw the easiest one, fluorine. Okay, so here's fluorine. So here's the nucleus of fluorine. It has 9 protons and neutrons. Okay, but I won't draw all of them. Okay, so I'll draw the electrons. 2 electrons in the innermost shell. And this next shell can hold 8 electrons. Okay. And so there are 7. And this is the valence shell. Okay. The valence shell likes to be either empty or full, and full would be 8 electrons. So what's the goal of fluorine in life?
To gain a valence electron to become ion.
To gain an electron and for the shell to become full. So what is fluorine going to talk to? Who wants to give up an electron? It'll talk to anybody who wants to give up an electron. Okay, all those first column elements, they want to give up 1 electron. So fluorine is real friendly with them. Okay, so in general, the elements on the right side of the periodic table want to gain electrons. The elements on the left side want to give up electrons. Okay, so the guys on the left will talk to the guys on the right. All right. All right, well, that was all a long story to tell you the following. Okay. So now we're interested in electric charges. Okay. Now, all atoms are neutral, but here's the deal. So here are materials that are willing to give up outermost electrons. And here are materials that want electrons. Okay. So if you rub these guys against these guys will give up electrons, and these guys will grab the electrons. That both will become charged. Okay. So if you, for instance, rub glass against silk. Silk wants an electron worse, even though, and glass is willing to give up its electron. Okay, if you rub glass against polyester, that's even better. Okay, so that's how you can charge objects. Now you've seen, you've heard of charges and so on before. Okay, like charges will repel each other. So if you have two positive charges, they'll repel each other, and a positive and a negative charge will attract each other. Okay, unlike charges will attract each other. All right, what are insulators and conductors?
Like just a general,
Mm-hmm.
I mean, an insulator like contains either like heat or energy.
Okay, so now we're talking about electrical insulators and conductors.
Contains the electrons from a state in a certain
So
path.
if you take a battery and connect an insulator, there won't be any current flowing, or the current will be very small. And if you have a conductor, the current will be large. Okay, so that's what we're talking about. Now, if any of you guys become material science engineers, you'll need to know this. But again, you'll learn this in a junior or senior level class, but we'll briefly talk about this. Okay, so here's an atom, and okay, again, here are the electrons. Okay. So this is a lower energy level, that's a higher energy level. Okay, so here are the energy levels of the electron. So here are the energy levels of the electron. Okay, in the lowest level you have 2 electrons, in the next higher level there, and so on. And this energy level is empty right now. Okay, you can excite the electrons from here to there. Okay, now what we're going to do is, we are feeling rich, so we'll get a whole bunch of atoms. Now we'll take a metal, for instance, okay, or any material, and all right, so let's consider a metal, for instance. And in a metal, the atoms are arranged in a regular pattern. Now, as soon as you take these atoms and arrange them in a lattice like this, in a metal, what happens to these energy levels is, these energy levels become bands. This energy level became that band. This energy level became that band. This energy level became that band. Okay, did you guys understand that? Now these bands themselves have many energy levels. Okay, each band has how many levels? If there are n atoms, each band has n levels. Okay. All right, so if you have an insulator, did you guys understand that? So you take a single atom and then you go to a lattice, these energy levels become bands. Okay, and now let's look at the bands. Okay. So now we'll talk about these bands of energy levels. Okay, so So this is a band gap. So these are bands, and this is a band gap. Okay, the lowest bands are all full. This is all full. Okay, oops, that's a band gap. Okay, and if this band is full and this band is empty, okay, this is the valence band, okay, and it's full. And if this band is empty, this material will be an insulator, okay, because for current to flow, you have to have electrons you have to have a partially filled band, okay. So for electrical conduction, you have to have a partially filled band. Okay. Now, if all right, so now let me draw another band. Okay, so if you have some electrons there, and okay, so this is again band gap, yeah, band gap. Okay, so this is called the conduction band. Okay, the topmost level that is partially filled is called the conduction band. Okay, so in conductors, this band gap is small. Okay, so at normal temperatures, at room temperatures, for instance, you have partially filled valence band and partially filled conduction band, and now this can be a good conductor. Okay, all right, so that's the difference between insulators and conductors from okay, so with the partially filled band, filled conduction band, electric current can be conducted, will flow through the material. Okay. All right, so now let me ask you this, okay. So let's say if you can excite more electrons from here to there, what will happen to the conductivity, you think? If there are more electrons to conduct, it'll become a better conductor. And that's what happens in semiconductors. You can change the carrier density, okay? So you can have low density and you can increase the density, okay? So those are, insulators have empty conduction bands, conductors have partially filled conduction bands, and semiconductors, you can vary the number of electrons in the conduction band, okay? By adding impurities and stuff like that, or changing temperature. So the number of free charges can be changed with impurities as well as temperature in semiconductors. Yeah. Again, you will learn about this eventually in your senior level classes or whatever, okay? But right now, we'll study the basics. Okay, now Mr. Coulomb studied the electrostatic forces between charged particles, and he figured out how strong the force would be. Yep. So for instance, if you have two positive charges, what will they do to each other? They'll repel each other. So if this guy repels with a force F, this guy will repel him with the equal and opposite force. Okay, and Mr. Coulomb figured out how strong this force will be. Okay, and Mr. Coulomb said, here's the magnitude of the force. Okay, it's constant times the product of the charges divided by the distance squared. Okay? And this is called the Coulomb's law, Coulomb's constant in his honor. Okay? And he used this device to figure that out, but this is called the Coulomb's constant. And if you go check your notes from the first semester, this is very similar to the gravitational force law. It's G m1 m2 divided by r squared. Okay. G is the gravitational constant. Here it's the Coulomb's constant. Okay. The Coulomb's constant happens to be much, much larger, so the electrostatic force is much stronger. Okay. All right, so in gravity, mass acts like the gravitational charge. Okay. All right. Now, the electric force happens to be very large, much larger than the gravitational force. Okay. So what this slide is showing you is the following. So if in the hydrogen atom, the proton attracts the electron, okay, well, it also gravitationally attracts the electron. So if you ask the question, let's say we'll calculate the gravitational force and the electrostatic force. Okay, how do these two forces compare? So for instance, in the hydrogen atom, do you guys understand the question? So this guy has a mass, this guy has a mass, it attracts him gravitationally, this guy has a charge, that guy has a charge, he attracts him electrostatically. So let's compare this force to that force. Now it turns out that in the hydrogen atom, that's the force between the proton and the electron. And between the proton and the electron, this is the gravitational force. If you take the ratio, it's 10 to the power 39. What that means is this force, 10 to the power of 39, is 1,000 trillion times larger. Okay, so this drawing is not to scale. What we are also saying is, if the electrostatic force is in play, okay, you can forget about the gravitational force. Okay. So the electrostatic force is much larger than the gravitational force. Yeah. Now, here's a second example. Okay, so here's a second example. If you take, you guys have seen a liter water bottle. If you take a liter water bottle and strip this water of all its electrons, now that's almost an impossible thing to do. So you essentially have 1 kg of protons. That's not true, you'll have half a kg of proton, but we'll say 1 kg of protons. And you have 1 kg of protons. What will they do? They'll repel each other. Okay, so I'm saying take this much water, here's another water bottle, strip it off all its electrons, and this guy of all its electrons. They will repel each other, and the repulsive force will equal the weight of the Earth. That's how strong the electrostatic force is. So of course, it's impossible, almost impossible to strip this guy of all its electrons. But if you could, that would be so the electrostatic force is very strong. Okay. All right. What the superposition principle states is the following. So if you have multiple charges, okay, this guy is repelling him and this guy is attracting him. Okay. So when you calculate the interaction of these two guys, you can ignore his presence. And when you calculate the interaction of these two guys, you can ignore his presence. Okay? So calculate the interactions independently, and then the sum of those forces is the net force on him. And that's the superposition principle. Okay? All right. So for instance, if you have many, many charges and there's your test charge, you calculate the interaction as independent pairs and then take the sum of all of that. So the 8 source charges each apply a force on the single test charge. Each force can be calculated independently of the other 7 forces. Yeah. All right. And what this slide shows you is that at the fundamental level, there's only 4 interactions. Okay? So there's only 4 forces in nature. The strong force, the electroweak force, or well, right now this is a combination of the two. So the electromagnetic force and the weak force, and the gravitational force. So we are studying the electromagnetic force right now. Actually, we're just studying the electrostatic force, but like I said, the electric and magnetic force are cousins. Okay, so that's lumped together as the electromagnetic force. This gives you the relative strength of these forces. If the strong force is 1 unit strong, the electromagnetic force is 100 times weaker. Okay. And the weak force is 1,000,000 times weaker, and the gravitational force is 10 to the minus 43 times weaker, which is very, 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 very weak. This gives you the range of the force. What does that mean? What do you think that means?
How far away you
Mhm.
can interact with.
That's right. So if two protons can interact via the strong force, so if they are 10 to the minus 14 meters away, then they can't see the strong force. The strong force has gone to 0. For them to interact via strong force, they have to be within 10 to the minus 15 meters. Okay? So now, did you guys understand that? Okay. So now this thing explains a couple of things. We've been drawing this. We've been drawing nuclei of atoms. So here's protons and neutrons. Okay. So here's the question for you guys. You just saw that the electrostatic force is quite strong. So here are 2 protons quite close by. Why aren't they repelling each other and flying apart?
Because they're too close to each other.
Well, the closer they are, the stronger the force. Remember Q1, Q2 divided by R squared. So smaller R is, bigger the force is. So why aren't the protons flying apart in the nucleus? Why should nuclei even exist? So that's what we just learned, okay? So, okay. The strong force is keeping them together. Okay, so the electrostatic force is repulsive. Okay. But the strong force, which is 100 times stronger, is keeping them together. Okay. So what does that tell you? That these guys have to be within 10 to the minus 15 meters. So the size of all nuclei roughly are about 10 to the minus 15 meters. Okay. So the size of all those nuclei in atoms are roughly that. Okay. Now, we've talked about this before, but anyway, so here is the nucleus. So the size of a nucleus is about 10 to the minus 15 meters, and now you know why the protons don't fly apart. The size of an atom is about 10 to the minus 10 meters. Okay? All right. So a nucleus is really tiny. So to give you a scale, if this and the atom were as big as a football stadium, the nucleus would be the size of a marble at the center. It would be that tiny. Okay. All right, so this tells you the range. So the strong force is the strongest, and it has a range of 10 to the minus 15 meters. The electromagnetic force is 100 times weaker, but it has an infinite range. The weak force is 1,000,000 times weaker than the strong force, and it has a very short range as well, 10 to the minus 18 meters. Okay, so to feel the weak force, you have to get really, really close. That's the size of a proton. Okay, less than the size of a proton. So you got to go inside the nucleus looking for the weak force. Okay. The gravitational force is got an infinite range as well. Okay. Now in the quantum theory, interactions are mediated by particles called bosons, and bosons have integer spin. Okay. And these are the particles that mediate the force. The strong force is mediated by gluons. The electromagnetic force is mediated by photons. The weak force is mediated by something called the W and Z bosons. And the gravitation presumably is mediated by graviton, but we haven't detected these guys. Okay. All right. This chapter has a lot of extra stories, but anyway, I think this is interesting enough, so I'll tell you about it. Okay. Okay. Before we do this, so let's say we take H2O. What is H2O? It's the compound H2O. And we are going to do everything at 1 atmosphere. Okay. Now, let's say we are at a temperature of 300 degrees Celsius. What is the state it is in?
Gas.
Steam, yep, gas. Okay. Then we're going to reduce the temperature. Okay. Let's say we reduce it to 90 degrees. Oh, well, we'll reduce it to 100 degrees Celsius. What starts happening? I'm sorry?
It starts condensing right back to
Yeah,
water.
so it'll start condensing. So you'll have some gas and some liquid. Okay. So what happens is as the temperature drops, a phase change happens, and you get multiple states. Okay. So similarly, so these 4 forces at very high energies were supposedly a single force. Okay. So just like this, only at low energies do we see it as different forces, as 4 forces. Okay. So this is what this diagram is telling you. Okay, so this is the Big Bang. This is 10 to the minus 50 seconds after the Big Bang. This is present day time. What is present day time?
4 forces.
No, yeah, this is 13.8 billion years after the Big Bang. Okay, so that's what that is. This gives you the temperature of the universe. At these temperatures, at the Big Bang, and this gives you the average energy of particles. Or okay, this is temperature in JeV units, in a different units. So at these high energies, it was a single force. When the universe cooled down to that temperature, the electroweak force separated from gravity. Okay? The electroweak and strong force separated from gravity. And when the universe had cooled down to that, the electroweak and the strong separated. Okay, when the universe had cooled down to that, the electroweak separated to electromagnetic and weak forces. And at these temperatures, you see them as 4 different forces. Okay, so that's what that is saying. All right. You have a question, Brock?
No, I never heard that explanation, like, from a phase change.
Mm-hmm. Yep.
I like that.
Yep, it is very neat. All right, so now we'll look at some properties of charges. Okay. Do you guys need a break? All right. I'll do a few more slides and then we'll take a 5-minute break. Okay. So properties of charges. Charge is conserved. What does that mean? The total charge of the universe is constant, whatever it is. Okay. And presumably it's 0. Okay. So no matter what you do, the charge of the universe will remain 0. Okay. So the total charge of the universe is constant, and as far as we know, it's 0. Okay. Charge is quantized. What that means is, in every charged object that we have seen, okay, this charge is an integer times the smallest charge. And this is the charge of the electron. Okay. So for instance, you can't go to Walmart and buy 3.14 charge of the electron. Okay. So you can only buy 4 electron charge, 5 electron worth charge, and so on. Okay. All right, so as far as we know, charge is quantized. Now, you will hear about, have you guys heard about quarks? Okay, so quarks have fractional charges, 130 and stuff like that, but you never see a quark by itself. You always see it in a bound state. So for instance, a proton is, I believe, has 2 up and 1 down quark. And so the charges combine to give you 1 E. Okay. All right. So for all particles that we see, the charge is always an integer multiple times the electron charge. Now, here's a very interesting chart table. Okay. So here's an electron, and as far as we know, an electron has no substructure. Here's a proton. It's got a positive charge, this got a negative charge. A proton is made out of quarks. A proton is about 2,000 times heavier than the electron. So needless to say, these guys are not related at all. They're not even cousins. Okay, very different particles. These guys are called hadrons. These guys are called leptons. But anyway, that's just names. Okay. Look at their charges. They're exactly equal. This is just a measurement up to a certain number of decimal places. As far as we know, the charges are exact to how many ever decimal places you want. Okay. How do we know that? You go outside, pick a handful of dirt. You have picked up an equal number of electrons and protons. And that dirt always has a 0 charge. Okay. So it's pretty amazing. Okay. All right. Now, we said that you go find any charged particle, and what we find is that its charge is always an integer multiple times the electron charge. Okay. Mr. Millikan established this. Okay. This was in 1909, and he won a Nobel Prize for that. Okay. And here's what the experiment was about. Here's how he did the experiment. So he had a spritzer, and he would spray oil droplets. Okay. And these oil droplets would fall, and they would fall and they would pretty soon gain terminal velocity. When do they gain? Why do they gain terminal velocity? Why does their speed not increase, keep increasing?
Is the air pushing?
Very good. So there's the force of gravity. And when do you gain terminal velocity? When the drag force equals that. Okay? So before they hit the plate, they gain terminal velocity. And from the terminal velocity, you can calculate the mass of the droplet. Yeah. And then what Mr. Milken would do was he would shine X-rays, ionize the air, and charge the oil droplets. Okay, so here's an oil droplet. He would put a charge on it. Okay, he would charge it, and then he would turn on an electric field in that direction. So it would have an electric force in this direction. That's balancing that. So now he's got it stopped. He's got it suspended. Okay. Remember, he got the mass from the terminal velocity. He turned on it, he gave it a charge, and then he had it suspended in air. All right, well, if it's suspended in air, E times Q, the charge on the oil droplet, is equal to M times G. You know this. You know the electric field. He knows how strong the electric field is. We know this. So you could calculate the charge on it. And he did this on thousands and thousands of oil droplets. And what he found was Q was always N times E. Okay? So the smallest charge he could detect was E for N equal to 1. Okay? And so that's how he found the charge of the electron and also the fact that charge was quantized. Okay? Now here's a YouTube video that I urge you guys to go see. Okay, there's a link, and you can see the Milken's oil drop experiment. All right, what we'll do is we'll pause now. You guys take a 5-minute break, and then we'll continue.